If you've ever stepped outside on a clear night and looked up, you've probably noticed that most of what we see, stars, constellations, the faint trail of the Milky Way, is still relatively close by on a cosmic scale. A few thousand light years here, a few tens of thousands there. Everything visible to the naked eye feels like it's part of our celestial neighborhood. But every once in a while, you meet something in the sky that genuinely breaks the local area rule. Something so big, so far, and so fundamentally different from everything else you can see without a telescope that it forces you to rethink what nearby even means in astronomy. That something is the Andromeda Galaxy, the nearest large galaxy to our own Milky Way, and the first stop for anyone trying to understand what galaxies actually are. Hi there, and welcome to Sleepy Space Traveler. I'm really glad you're here, and I hope this moment can become a pause in your day. This channel was created as a quiet space for anyone who enjoys falling asleep to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. Here, we slow everything down. We take big ideas about space, time, reality, and existence, and turn them into simple, soothing stories you can drift off to. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space, and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from, and what time it is for you right now. And wherever you are, maybe lying in bed, settling into the night, or just looking for a moment of calm, I hope this time feels peaceful. I hope your mind can soften, your breathing can slow, and your body can rest. Thank you for being here. Now, let's begin. Andromeda isn't just another smudge in the sky. It's a massive, complex, gravitationally self-contained city of stars. It's a cosmic metropolis with 1 trillion residents, and it has been quietly hanging out in our night sky for millions of years, patiently waiting for Earth's inhabitants to invent telescopes, physics, and a basic understanding of the universe so we could finally begin to appreciate it properly. Andromeda also plays a special role in the way humans came to understand the universe. A little over a century ago, astronomers still debated whether Andromeda was a spiral nebula inside the Milky Way or a separate island universe, the term used in the early 20th century for what we now call galaxies. Edwin Hubble famously settled the debate in the 1920s by identifying Cepheid variable stars within Andromeda and calculating their distance. The result? Andromeda wasn't just outside the Milky Way, it was far outside it, at a scale no one had seriously considered before. Overnight, the size of the universe expanded in the human imagination by unimaginable orders of magnitude. So, when we talk about the Andromeda Galaxy, we're not just discussing an astronomical object. We're discussing a key discovery that literally changed the shape of the universe in our minds. Why Andromeda matters. You might wonder, with billions of galaxies out there, why focus so much attention on this one? Why is Andromeda so special compared to the countless galaxies astronomers can observe through high-powered telescopes? There are a few reasons. 1. It's close. At roughly 2.54 million light-years away, Andromeda is practically next door in cosmic terms. In fact, it's so close that it's approaching us, moving at about 110 km/s. If the universe were a city, Andromeda would be the slightly larger neighboring district that you're slowly drifting closer to every year. You can't ignore it. It's too big, too close, and it's headed your way. 2. It's enormous. Andromeda is one of the largest galaxies in the local group, and likely larger than the Milky Way. It contains about 1 trillion stars, roughly double what our galaxy is estimated to have. That alone makes it a perfect case study for understanding galactic structure and evolution. 3. It's a cosmic laboratory. Because it's so nearby, astronomers can observe details in Andromeda that are simply impossible to see in most other galaxies. We can study individual stars, clusters, gas clouds, dust lanes, and spiral arm structures with remarkable clarity. That makes Andromeda one of the best test subjects for theories about galaxy formation, dark matter distribution, star formation, and galactic dynamics. 4. It's our future dance partner. In about 4 to 5 billion years, the Milky Way and Andromeda will collide and merge into a new galaxy, often referred to as Milkomeda or Milkdromeda. This isn't going to be a dramatic Hollywood-style explosion, but a long, graceful gravitational interaction that takes hundreds of millions of years. Understanding Andromeda today helps scientists model what that future merger will look like. In short, Andromeda is the friend, neighbor, rival, and future spouse of our galaxy, all at once. It's hard not to pay attention to it. Let's start with the basics. What does Andromeda actually look like? To the naked eye, under very dark skies, it appears as a hazy, elongated smudge. It doesn't look like much, but that faint glow is the combined light of hundreds of billions of stars. The surprising thing is that Andromeda is already bright enough to see without equipment. If it were just a little closer, it would dominate the night sky the way the full moon does. Through telescopes, its shape becomes clearer. A majestic barred spiral galaxy with sweeping arms, a bright central bulge, and extensive dust lanes that twist and curve around its disk. When photographed by observatories like Hubble, Andromeda reveals itself as one of the most structurally beautiful galaxies in our cosmic neighborhood. It's not just a disk of stars, it's an entire gravitational ecosystem. Let's break down what astronomers mean when they talk about Andromeda's structure, the anatomy of the Andromeda Galaxy. Just like cities have distinct neighborhoods, downtown districts, suburbs, industrial zones, galaxies have their own structural components. They aren't just random clouds of stars. They have order, architecture, and predictable dynamics that reveal how they formed and evolved. Andromeda contains all the classic components of a spiral galaxy. Understanding these will not only help us make sense of Andromeda, but will also help us understand the Milky Way and many other galaxies. 1. The galactic bulge. At the center of Andromeda is a bright, dense concentration of stars known as the bulge. If you think of the galaxy as a giant spinning pancake, the bulge is the slightly puffed-up center. This region is packed with older reddish stars, dominated by complex stellar orbits, extremely bright, home to a central supermassive black hole. In Andromeda's case, its black hole is about 100 million times the mass of our Sun, which is significantly larger than the Milky Way's central black hole, Sagittarius A, which weighs in at around 4 million solar masses. Stars in the bulge move in many different directions. It's a chaotic space where the history of past mergers is written into the motion of the stars. If the galaxy were a library, the bulge would be its archive of ancient records. 2. The disk and spiral arms. The disk is the broad, thin region where most of Andromeda's stars, gas, dust, and star-forming regions reside. Spiral galaxies are defined by their arms, and Andromeda's arms are particularly striking, though slightly asymmetric due to past interactions with smaller galaxies. The disk contains star-forming regions, dense molecular clouds, bright blue clusters of young stars, dust lanes that appear as dark streaks. To visualize the spiral structure, think of a traffic flow around a circular highway. Cars, stars, move individually, but traffic jams, density waves, happen in predictable patterns. Similarly, spiral arms aren't solid structures. They're regions where stars and gas temporarily bunch up due to gravitational influences. Astronomers use infrared and ultraviolet observations to study different parts of the disk. Ultraviolet highlights young, hot, blue stars. Infrared reveals older stars and dust obscured by gas clouds. Radio observations reveal hydrogen gas, the raw material for new stars. This multi-wavelength approach gives a complete picture of how Andromeda builds stars, distributes mass, and evolves over time. 3. The halo. If you only looked at visible light images, you might think that Andromeda ends where its brightness fizzles out. But galaxies have extended halos that stretch far beyond the visible edges. These halos are enormous, faint spheres of ancient stars, globular clusters, dark matter, and tidal debris from past mergers. Andromeda's halo is enormous, much larger than the visible disk, and holds clues about its long, cannibalistic history. Some of the halo's stars are older than the galaxy's main disk, and many appear to have originated in smaller galaxies that Andromeda consumed. Globular clusters, dense spherical star clusters, float throughout the halo like celestial beacons, and Andromeda boasts over 450 of them, more than twice as many as the Milky Way. But the most significant component is dark matter, the invisible mass that shapes the galaxy's gravitational field. Andromeda's halo contains far more dark matter than regular matter. Without it, the galaxy wouldn't be able to hold itself together at the rotation speeds we observe. 4. The central black hole. Every major galaxy seems to have a supermassive black hole at its center, and Andromeda is no exception. Andromeda's central black hole is massive, more than 20 times the size of the Milky Way's. This black hole affects the motions of nearby stars and influences the shape of the central bulge. It is currently quiet, meaning it's not actively feeding on large amounts of gas. If it were, we would see bright jets and energetic emissions. Instead, like the Milky Way's black hole, it sits quietly, an enormous but dormant gravitational anchor. Galaxies don't stay static over billions of years. They merge, collide, strip material from neighbors, and grow through gravitational interactions. Andromeda has a rich and somewhat dramatic history of merging with smaller galaxies. These events leave behind subtle signatures, streams of stars that arc through the halo, distorted spiral arms, variations in star populations across the disk. One particularly telling clue is the presence of stellar streams, thin, elongated groups of stars that arc around Andromeda. These streams are the remnants of dwarf galaxies that Andromeda absorbed long ago. In fact, recent studies suggest that Andromeda may have undergone a major merger around 2 billion years ago. long after the Milky Way had already settled into its current structure. This could explain why Andromeda's disk appears somewhat warped, and why some regions show bursts of relatively recent star formation. Andromeda. Compared to the Milky Way, to understand Andromeda, let's compare it with our own galaxy. Similar in type, both are large spiral galaxies, but Andromeda is bigger overall. Estimated 1 trillion stars in Andromeda. Milky Way holds about 400 billion stars. Andromeda's disk, wider and more extended. Visible diameter, about 140,000 light-years. Milky Way's diameter, about 100,000 light-years. Andromeda's halo, more massive, more populated with old stars. Star formation, active in both, but Andromeda shows distinct rings. Milky Way's structure, more symmetric. Andromeda's structure, more disturbed, evidence of past mergers. Central bulges. O, Andromeda's larger and brighter. O, Milky Way's more compact. Supermassive black holes. O, both around millions of solar masses. O, Andromeda's appears more massive. Satellites. Both galaxies have dwarf companions. But Andromeda's group is more populated. Motion. Andromeda is moving toward us. Predicted collision in 4 or 5 billion years. Result, likely a merged elliptical galaxy nicknamed Milkdromeda. The key takeaway, Andromeda is probably the heavyweight champion of the local group. For decades, we believed it was unquestionably larger and more massive than the Milky Way. Newer studies suggest the Milky Way may be more massive than previously thought. But Andromeda is still bigger in terms of diameter and star count. The fact that Andromeda is approaching the Milky Way is one of the most striking aspects of our relationship with this galaxy. Despite the expansion of the universe, gravitationally bound systems can still move toward each other. The Andromeda Galaxy is moving toward us at about 110 km per second, or roughly 250,000 miles per hour. This may sound alarming, but the collision is far in the future, about 4 to 5 billion years from now. This motion has been carefully measured using the Doppler shift of its spectral lines, the proper motion of stars measured by Hubble and Gaia, long-term tracking of Andromeda's trajectory. Understanding Andromeda's motion not only helps us predict the future merger, but also provides insights into how dark matter shapes the dynamics of the local group. Even though Andromeda is the closest large galaxy to us, it's still 2.54 million light-years away, a distance so large that it challenges our intuition. You can't fly there, you can't send a probe there, and you certainly can't visit it on a casual weekend trip. That means everything we know about Andromeda comes from the same thing humans have relied on for centuries: light. Light is our messenger. It carries information across unfathomable distances, arriving on Earth long after it has left its source. Studying a galaxy is like reading a letter that took millions of years to arrive. Andromeda's light began its journey long before humans existed, before Earth had mammals, before the continents were even close to their modern shapes. And yet, that ancient light now streams into our telescopes every night, giving us a way to understand something profoundly distant. But light doesn't just mean the stuff we see with our eyes. The electromagnetic spectrum is huge, and all of it is useful. If the universe were a crime scene, each section of the spectrum would be a different kind of forensic tool. Visible light may be the magnifying glass, but X-rays are your chemical trace detector, infrared is your heat scanner, and radio waves are the long-range surveillance microphones that pick up quiet whispers. To understand Andromeda properly, astronomers use all these tools. Let's start with the most familiar type: visible light. Even through a backyard telescope, Andromeda looks beautiful, an elongated, glowing ellipse with hints of structure. But professional telescopes, especially space-based observatories like Hubble, reveal far more detail. Sharp dust lanes curving around the disk, bright clusters of young blue stars, the distinct bulge glowing in the center, hints of spiral structure, subtle asymmetries that betray a turbulent past. Visible light gives us the classic photograph of Andromeda. It's like seeing the exterior of a city from an airplane window. You get a good sense of layout, brightness, and shape. But you're not yet seeing the fine details inside. One important thing visible light shows us is color differences across the galaxy, which reveal age. Blue stars, young, hot, recently formed; yellow stars, middle-aged red stars, older, cooler stars. The visible spectrum tells us Andromeda is actively forming stars in some regions, blue clumps, and aging gracefully in others, yellowish bulge, redder halo stars. But visible light is only the beginning. Dust in space is annoying for astronomers. It blocks light, hides star-forming regions, and makes galaxies look like someone smeared grease on the camera lens. But dust does something useful. It absorbs light and re-emits it as infrared radiation. Infrared telescopes like Spitzer, the James Webb Space Telescope, JWST, and ground-based infrared observatories let astronomers see through the dust and reveal stars hidden in dusty regions, the distribution of cooler stars, the structure of Andromeda's bar and inner disk, molecular clouds where new stars will eventually form infrared views show a smoother, more mature Andromeda, a galaxy whose underlying structure becomes clearer once the cosmic fog is removed. JWST, in particular, has taken the sharpest infrared images of Andromeda ever obtained. In IR light, the galaxy glows with the soft structure of its older, cooler stars, making its spiral design undeniable and elegant. It's like switching from a regular photo to a thermal scan. Suddenly, the underlying framework appears. Infrared also helps astronomers map the mass of Andromeda, not just the bright young stars. Ultraviolet, UV, light highlights something specific: hot, young, massive stars. These stars live fast and die young, burning through their fuel in a few million years. Because of that, UV maps give astronomers a real-time snapshot of where star formation is happening right now. Andromeda's ultraviolet maps reveal bright star-forming rings, clusters of short-lived blue giants, pockets of recently ignited stars across the disk. Interestingly, Andromeda has a large, well-defined ring of UV emission, which suggests a past gravitational interaction, likely with one of its satellite galaxies, triggered a wave of star formation. If visible light shows us a city skyline, UV shows us where the newest construction is happening. Radio astronomy is how we detect neutral hydrogen gas, HI, the basic fuel for star formation. Neutral hydrogen emits at a very specific wavelength, 21 centimeters, which radio telescopes pick up easily. Radio maps of Andromeda tell us how gas flows through the galaxy, where future star formation could happen, how spiral arms move, details of Andromeda's rotation curve, important for dark matter. The 21-dome hydrogen line is one of the most powerful diagnostic tools ever discovered in astronomy. It lets scientists trace material that doesn't glow in visible light. Radio telescopes also detect molecular gas, carbon monoxide, CO, synchrotron emission from high-speed electrons, cold dust invisible to optical instruments. This means radio astronomy paints the skeleton and bloodstream of the galaxy. X-ray observations show us the hottest, most energetic processes: black hole activity, neutron stars, supernova remnants, hot gas in the halo. Andromeda is unusually bright in X-rays, suggesting an abundance of accreting black holes, white dwarfs siphoning material from companion stars, shock-heated gas from past collisions. Chandra X-ray Observatory and XMM Newton have mapped hundreds of X-ray point sources in Andromeda. Many of these are binary star systems where a compact object, like a neutron star, pulls material off a companion, heating it until it emits high-energy radiation. X-rays show us Andromeda's extreme sports division, the violent, high-energy side of a galaxy that otherwise looks serene in visible light. One of the most important parts of Andromeda's historical role is that measuring its distance expanded our sense of the universe. But how do we measure the distance to something millions of light-years away? Astronomers use multiple methods, cross-checking them like a cosmic accountant trying to avoid mistakes. 1. Cepheid variables. Cepheids are pulsating stars whose brightness rises and falls in a predictable pattern. The period of their pulsation tells you their true luminosity. Compare that to how bright they appear, and you can calculate distance. Edwin Hubble used Cepheids in Andromeda to prove it lies far outside the Milky Way. 2. Red giant branch fitting. Red giants reach a maximum brightness before undergoing helium ignition. This tip of the red giant branch, TRGB, has a known luminosity, making it another reliable distance indicator. 3. RR Lyrae stars. Older, fainter pulsating stars, useful for mapping distances to globular clusters in Andromeda's halo. 4. Surface brightness fluctuations. Nearby galaxies show slight statistical variations in brightness across their surface. The closer the galaxy, the larger the fluctuations. This method works well for Andromeda. 5. Type Ia supernovae, rare but extremely bright, they act as standard candles. Andromeda has hosted several historic supernovae recorded in ancient texts. By combining all these methods, scientists now estimate Andromeda's distance with remarkable precision, 2.4 plus 0.11 million light-years. Now we get to something fascinating. Andromeda rotates too fast. When astronomers measured the rotation curve, the speed of stars as a function of distance from the center, they discovered something strange. Stars far from the center orbit at roughly the same speed as stars closer in. That shouldn't happen if only visible matter were present. The rotation curve stays flat instead of declining. This tells us there is far more mass in Andromeda than we can see. That mass forms a huge, invisible halo. Dark matter is real and necessary to explain how galaxies behave. Without dark matter, Andromeda would fly apart. Rotation curves are one of the strongest pieces of evidence for dark matter in the universe, and Andromeda is one of the best studied examples. Astronomers classify stars and galaxies into different populations based on age, composition, and location. Andromeda contains population Watson stars, young, metal-rich, found in spiral arms, star-forming regions, bright blue clusters. These stars reveal current galactic activity. Population test stars, old metal poor, found in halo, globular clusters, bulge. These stars preserve the early history of Andromeda's formation. By comparing these populations, astronomers reconstruct Andromeda's timeline. When major mergers happened, how fast star formation proceeded, how the galaxy accumulated its mass, whether its structure has changed over billions of years. Andromeda's mix suggests a galaxy that was once extremely active and has undergone several major mergers, some of which may still be ongoing. If you look at a picture of Andromeda today, wide spiral arms, bright core, elegant structure, it's easy to imagine a calm and stable cosmic city, something that has always looked this way and always will. But the truth is far less peaceful. Galaxies are dramatic creatures. They collide, they steal from each other, they grow by devouring their neighbors, and sometimes they reshape themselves in ways that would make a city planner faint. Andromeda is no exception. In fact, it's one of the most active galaxies in our cosmic neighborhood. It has a long history of galactic collisions and mergers, some of which still leave visible scars across its structure. To really understand Andromeda, we have to look past the pretty facade and understand the chaotic, gravitationally fueled drama that shapes its evolution. Think of the last part as Andromeda's biography of past relationships, the good, the bad, and the gravitationally destructive. Astronomers once believed Andromeda was a quiet spiral galaxy, similar to the Milky Way. Smooth rotation, predictable structure, well-behaved stars. But observations over the last decade have rewritten that narrative. New data, especially from the Hubble Space Telescope, the Gaia mission, and deep sky surveys, has revealed that Andromeda is the survivor of multiple galactic mergers. The evidence appears everywhere, in the way its halo is shaped, in the clumps of stars orbiting around it, and even in the unusual patterns within its spiral arms. A 2018 study using Gaia data revealed that at least one major galaxy smashed into Andromeda around 2 billion years ago. That's not just a light bump. That's the kind of collision that would completely restructure a galaxy. Imagine two massive, star-filled disks colliding at hundreds of kilometers per second. Stars don't typically crash into each other. The distances are too big. But the gravitational forces rip everything apart and reassemble it into a new galaxy. It's like cosmic demolition followed by cosmic remodeling. This helps explain why Andromeda's spiral structure looks lopsided compared with the Milky Way's relatively symmetric formation. It's the gravitational echo of a very messy past. One of the clearest indicators of Andromeda's violent history is its halo, a vast, diffuse sphere of stars, gas, and dark matter that surrounds the main disk. In many ways, the halo acts as a fossil record of everything a galaxy has eaten. The Milky Way's halo is modest and somewhat sparse. Andromeda's halo, on the other hand, is enormous. It stretches far beyond its visible disk and is filled with streams of stars that appear to be the remains of small galaxies that Andromeda absorbed. Astronomers have identified dozens of star streams weaving through Andromeda's halo. These are long, thread-like formations made of stars that were once part of smaller dwarf galaxies before gravitational stretching tore them apart. A 2020 study using the Canada-France-Hawaii Telescope, CFHT, found that 1/3 of all the stars in Andromeda's halo came from a single massive dwarf galaxy that Andromeda devoured roughly 2 billion years ago. They even gave the long-lost galaxy a name, M32P. Andromeda's halo is so massive and complex that it implies Andromeda has swallowed many more galaxies than the Milky Way. If the Milky Way is a picky eater, Andromeda is a galactic buffet enthusiast. If you look at infrared or ultraviolet images of Andromeda, you'll notice something interesting. The spiral arms aren't just arms. They look more like separate rings. Especially a large ring roughly 10,000 light-years from the center and another around 38,000 light-years out. These rings are unusual. The Milky Way doesn't have them, and typical spiral galaxies do not show such well-defined circular structures. So what could create them? One explanation is a past collision. Perhaps a smaller satellite galaxy plunged through Andromeda's disk, disturbing the gas and dust and initiating waves of star formation. This is similar to dropping a pebble into a pond and watching the ripples expand outward. Simulations show that a direct hit from a companion galaxy, possibly M32 or another long-absorbed satellite, could generate ring-like star formation patterns that persist for hundreds of millions of years. Andromeda's rings aren't perfect circles either. They're slightly offset, indicating the collision wasn't centered. It's like someone flicked the galaxy from an angle and the rings never fully settled. These rings help astronomers map Andromeda's internal physics, revealing where gas clouds compress, ignite, and form new stars. In other words, Andromeda's past collisions continue to shape its present-day stellar growth. One of the most fascinating pieces of evidence for Andromeda's violent history is the tiny but unusual galaxy M32, which orbits very close to Andromeda's core. M32 is strange because it is compact, dense, and unusually bright for its size. For decades, astronomers had no clear explanation, until simulations suggested that M32 may actually be the bare core of a once much larger galaxy. Andromeda appears to have stripped away almost all of M32's outer stars during a past merger, leaving behind the concentrated center. It's essentially a galactic skeleton. Other satellite galaxies also show signs of disruption. Several appear elongated or distorted as if they're being stretched by Andromeda's gravity, preparing to be absorbed in the future. In fact, Andromeda is currently in the process of pulling apart several small dwarf galaxies. It's not doing this maliciously. Gravity just does what gravity does. But the result is the slow, inevitable consumption of surrounding cosmic neighbors. Andromeda's history is not shaped only by visible stars and gas. A huge portion of its gravitational behavior comes from something we can't see at all: dark matter. Dark matter forms a massive halo around Andromeda, possibly extending hundreds of thousands of light-years beyond the visible galaxy. This invisible structure shapes how Andromeda rotates, how it merges with smaller galaxies, how star streams form, how long the galaxy can maintain its shape. The Milky Way also has a dark matter halo, but Andromeda's appears to be significantly larger and denser. This is one of the main reasons astronomers think Andromeda has grown more quickly and eaten more galaxies over time. Without dark matter, Andromeda's motion wouldn't make sense. Its stars orbit far faster than gravity from visible matter alone could support. In physics terms, the outer stars should be flung off like mud from a spinning tire. But they aren't, because dark matter's gravitational pull holds everything together. In this sense, dark matter is the hidden architect behind Andromeda's past and future. Beyond stars and rings and halos, Andromeda contains hundreds of globular clusters, dense, spherical groups of stars that orbit the galaxy like tiny beacons of ancient history. Some of these clusters show chemical signatures that don't match Andromeda's native population. They are clues that these clusters originally formed in smaller galaxies before those galaxies merged into Andromeda. These clusters are like survivors of galactic battles, small, tightly bound, and durable. While merging galaxies are torn apart, their globular clusters often remain intact, drifting into new orbits and living on as historical markers. Their chemical fingerprints allow astronomers to reconstruct Andromeda's family tree, when mergers occurred, how large the incoming galaxies were, and how dramatically they changed Andromeda's structure. A galaxy is not just stars and dark matter. It contains complex weather systems, flows of gas, giant clouds of dust, shock waves from supernova explosions, and magnetic fields twisting through space. Andromeda's gas distribution is particularly interesting. Its central region has less cold gas than the Milky Way. The outer disk has patches of dense gas where new stars form. The inner region shows signs of winds from past starburst activity. These observations support the theory that a major merger triggered a burst of star formation a few billion years ago, consuming much of the available gas near the center. Today, Andromeda forms new stars more slowly than in its youth, roughly 1 solar mass per year, compared to the Milky Way's 1 to 2 solar masses per year. The difference isn't huge, but it suggests that Andromeda is gradually transitioning into an older, quieter galaxy, like a fire that has burned brightly but is now settling into embers. At the heart of Andromeda lies a supermassive black hole, much like the Milky Way's Sagittarius A. But Andromeda's black hole is believed to be significantly larger, possibly 100 million solar masses, compared to the Milky Way's 4 million. Surprisingly, Andromeda's black hole is relatively quiet. It doesn't emit large jets or flare brightly in X-ray wavelengths. This calm behavior suggests it isn't currently feeding on much gas or dust. But that doesn't mean it has always been quiet. Evidence of past energetic events, such as shock waves and unusual patterns of hot gas, suggests the black hole may have been more active in earlier epochs, possibly triggered by inflows of gas during past mergers. Astronomers believe that during the Milky Way-Andromeda collision 5 billion years from now, both galaxies' central black holes will eventually spiral inward and merge, releasing a massive burst of gravitational waves. It will be one of the greatest fireworks shows in the history of the local group, though no humans will be around to see it. Putting all of this together, Andromeda is not a static picture, but a dynamic, evolving system. Its current structure is the product of billions of years of interactions, and it continues to change even now. Today, it sits in a relatively quiet phase. No major collisions imminent, star formation slowly decreasing, satellite galaxies gradually being absorbed. But its future holds dramatic events, starting with its collision with the Milky Way. For most of human history, the night sky has looked steady and reliable. The stars appear fixed, the constellations repeat their patterns, and the Milky Way stretches overhead like a quiet river of light. Nothing about that scene suggests that our entire galaxy is in motion, heading toward another enormous galaxy in a slow, 5 billion year-long dance that ends in a cosmic merger. Yet that is exactly what is happening. Right now, the Milky Way and Andromeda are connected not only by gravity, but by fate. The collision between our galaxies is not hypothetical. It is not a guess, a possibility, or a maybe. It is a scheduled event in cosmic time, as guaranteed as the sun eventually running out of fuel. The only reason it feels unbelievable is because our lives are too short to witness even a fraction of the process. The Andromeda Milky Way collision will be the largest gravitational event in the history of our local group. And despite how dramatic the phrase galactic collision sounds, the truth is surprisingly gentle and surprisingly beautiful. Now we will walk you through the science of what happens when two galaxies collide, why this collision is inevitable, and how astronomers model the entire process using simulations, physics, and the motion of stars. Andromeda is currently 2.5 million light-years away, but that distance alone doesn't tell the whole story. The key scientific evidence comes from measurements of its motion. Using the Hubble Space Telescope, astronomers measured that Andromeda is moving toward the Milky Way at about 110 kilometers per second, fast enough to cross the continental United States in under a minute. Although space is vast and distances are enormous, speed like that adds up over millions of years. Before Hubble confirmed this approach, some scientists suspected Andromeda might be moving sideways, not inward. But precise measurements removed all doubt. Andromeda is coming straight for us on an intercept course. Still, we shouldn't pack our cosmic evacuation bags anytime soon. At its current speed, it will take roughly 4 to 5 billion years before the galaxies physically overlap. The collision will unfold slowly from a human perspective, but rapidly in cosmological terms. If the entire timeline of the universe were shrink-wrapped into a single year, the collision would take only a few seconds. The word collision conjures images of stars smashing together like billiard balls. Fortunately, that does not happen. Space inside galaxies is mostly empty. Even inside the dense spiral arms, the distance between stars is so large that if the sun were the size of a marble, the nearest star would be another marble more than 300 miles away. So, when the Milky Way and Andromeda collide, the stars pass through one another almost effortlessly. The real chaos happens in the gravity. Gravity builds up during the collision like tension in a rope being twisted. Gas clouds crash, shock waves form, star formation explodes, spiral arms stretch and twist, and the galaxies tear each other apart while simultaneously blending together. A galactic collision is less like a car wreck and more like two vast clouds of fireflies drifting into each other. Except the fireflies have gravitational pull and can reshape each other's motion. Let's break the process down into stages. Stage 1. First contact, about 4 billion years from now. As Andromeda approaches, it will appear to grow larger and brighter in our night sky. Right now, it's just a faint smudge without a telescope. But a few billion years from now, it will be spectacular, spanning many times the width of the moon. When the outer halos touch, gravitational tides begin to warp both galaxies. The Milky Way's spiral arms may begin to twist, while Andromeda's rings and arms distort dramatically. At this point, star formation will surge as gas clouds compress. Massive shock fronts will form between colliding gas regions. Stars will be flung into long arcs called tidal tails. This stage doesn't destroy either galaxy, but begins the long process of transforming them. Stage 2. The interpenetration, The first pass-through. A few 100 million years after the first contact, Andromeda will plunge through the Milky Way's disk. Because neither galaxy is solid, they pass through each other like ghosts, but leave behind gravitational chaos. During this phase, the centers of both galaxies will overshoot each other. Stars in both galaxies will be scattered into elongated orbits. Gas clouds will collide, triggering massive starbursts. Long tidal tails will extend tens of thousands of light years. The night sky from a planet inside one of these galaxies would become breathtaking. Imagine a sky dominated by bright arcs of stars, dust clouds glowing from newborn star clusters, and Andromeda's core hanging overhead like a glowing chandelier. Stage 3. The oscillation and spiral. After the first pass-through, gravity pulls the galaxies back together. They swing around each other, slow down due to drag from dark matter and gas interactions, and spiral inward like two dancers losing momentum but drawn by each other's weight. This oscillation may happen 2 or 3 times, each pass-through blending the galaxies more deeply. With each cycle, the distance between their cores shrinks. Eventually, the 2 central bulges settle toward one another and merge into a single gravitational center. Stage 4. The black hole merger. Both galaxies contain supermassive black holes. Milky Way, 4 million solar masses. Andromeda, 100 million solar masses. As the galaxies merge, their black holes fall toward the center of the newly forming galaxy, orbiting each other in a tightening spiral. Eventually, they will collide and merge in an event so powerful it sends gravitational waves rippling across the universe. No one will be around to witness it, but the universe will hear it through space-time itself. Stage 5. The final result, Milkdromeda. After the gravitational dust settles, likely 6 to 7 billion years from now, the Milky Way and Andromeda will no longer exist as separate spiral galaxies. Instead, they will form a single, enormous elliptical galaxy. Astronomers have informally named it Milkdromeda, a charming blend of Milky Way and Andromeda. Alternatively, some researchers prefer Milkomeda, which sounds slightly more dramatic but equally fun. This final galaxy will be at least 2 and 3 times larger than either original galaxy, filled with redistributed stars, lacking traditional spiral arms, surrounded by an enormous merged halo. In other words, a brand new supergalaxy formed from the quiet cosmic drift of 2 old ones. Will the solar system survive the collision? The short answer, probably. The long answer is more interesting. There is about a 70% chance that the Sun will be flung into a new orbit around the center of Milkdromeda, one that may carry it farther from the central bulge than it is today. There is also a smaller chance, a few percent, that the solar system may be ejected entirely into intergalactic space. Not dangerous, just very lonely. However, none of this will matter for life on Earth. By the time of the merger, the Sun will be nearing the end of its habitable period. Earth's oceans will have boiled away due to rising solar luminosity, and life as we know it will no longer be possible. If humanity survives until then, it will likely be starfaring, living on artificial habitats or distant colonies. The cosmic light show of a galactic merger could be the most spectacular backdrop imaginable for future civilizations. Although the Milky Way-Andromeda collision sounds dramatic, it is a normal part of galaxy evolution. Most large galaxies have undergone multiple mergers. The Milky Way has eaten dozens of dwarf galaxies. Andromeda has absorbed even more. Massive galaxy clusters show evidence of countless mergers. In fact, without mergers, galaxies would remain small and dim. Collisions fuel star formation, build up mass, and reshape galaxies into new forms. If galaxies behaved politely and never collided, the universe would be a much darker place. Galactic collision predictions rely on 1. Precise motion data. The Gaia spacecraft tracks motions of stars in the Milky Way with micro-arcsecond precision, allowing scientists to understand our galaxy's velocity and structure. 2. Hubble proper motion measurements. Hubble measured Andromeda's sideways motion, which had been unknown for decades. Once astronomers knew the direction and speed, the collision timeline became clear. 3. Supercomputer simulations. Simulations model billions of particles representing stars, gas, and dark matter. These simulations consistently show the galaxies will collide, they will merge, the result will be an elliptical galaxy. These predictions are robust across a wide range of assumptions. Despite the grand scale and immense gravitational forces, a galaxy merger is not something that tears apart stars or destroys civilizations through direct collision. Instead, it is a slow, elegant dance, chaotic in some ways, but profoundly beautiful. It is a reminder that the universe is always changing, always reshaping itself, even when we cannot see the process. From Earth, the night sky feels timeless, but our galaxy is already part of a long, unfolding chain of events that will eventually erase its distinct identity and blend it with another. In a sense, we live inside a story that began billions of years before Earth formed, and will continue billions of years after Earth is gone. In the next part, we will zoom back out, exploring Andromeda's place in the local group, how its gravity influences satellite galaxies, and how the entire local group will eventually merge into one giant structure. When we talk about the Milky Way and Andromeda, it's easy to think of them as isolated giants floating alone in the cosmos. But galaxies rarely live solitary lives. They gather in social clusters, much like people do. The Milky Way and Andromeda are the two largest members of one such community. The local group, a gravitational neighborhood about 10 million light-years across. This part zooms out and explores Andromeda's role in the local group, how it shapes its surroundings, how it interacts with its smaller companions, and how the entire region will evolve over trillions of years. If the last part was about the future collision between two galaxies, this part is about the fate of dozens. The local group consists of the Milky Way, Andromeda, M31, the Triangulum Galaxy, M33, around 60-plus dwarf galaxies. The whole structure is held together by gravity, a weak force individually, but overwhelmingly powerful on galactic scales. If galaxy clusters were cities, the local group would be more like a small town. It's not densely packed like the Virgo cluster, where galaxies crash and interact constantly. Instead, it's relatively quiet, with plenty of space between members. Yet, even in this cosmic suburb, Andromeda plays an outsized role. While the Milky Way may feel like the center of the universe to humans, because it hosts us and all of human history, it is actually the second largest galaxy in the local group. Andromeda is bigger, heavier, and more structurally dominant. Andromeda's mass. There are 1.5 trillion solar masses. Milky Way's mass. As in 1 trillion solar masses. This difference might not sound dramatic, but it profoundly affects the local group's dynamics. Andromeda's stronger gravitational influence is one reason the Milky Way is moving toward it, rather than drifting away. In galactic terms, Andromeda is the gravitational anchor of the local group. Its gravity shapes the motions of dwarf galaxies in its orbit, the long-term paths of free-floating dark matter, the future trajectories of the Milky Way and Triangulum, the eventual merging of the entire local group. Think of Andromeda as the largest object at a family gathering. Even if it doesn't talk much, everyone orbits around its presence. Surrounding Andromeda is a swarm of small dwarf galaxies, little islands of stars, dust, and dark matter. Some are orbiting steadily. Others are being torn apart by Andromeda's gravity, leaving behind long tidal streams. Dwarf galaxies around Andromeda include M32, a compact elliptical, likely the stripped core of a galaxy Andromeda 8. M110, another elliptical dwarf, showing signs of distortion. NGC 147 and NGC 185, a binary pair orbiting together. Dozens of ultra-faint dwarfs, some so dim they were discovered only in the last decade. Andromeda's dwarfs reveal a remarkable truth. Large galaxies grow by consuming smaller ones. Evidence of past meals is etched into Andromeda's halo, where astronomers have found star streams, shells of stripped material, elongated arcs of disrupted dwarf galaxies. These features are the leftovers of galaxies that came too close to Andromeda and were shredded. Astronomers believe Andromeda has consumed hundreds of dwarf galaxies over billions of years. This is not unusual. It's how galaxies evolve. The Milky Way does the same thing. In a cosmic sense, cannibalism is normal. Triangulum is the local group's third largest member, though calling it large is generous. Compared to Andromeda and the Milky Way, it's more like a younger sibling tagging along. Triangulum is about 60,000 light-years across, a beautiful spiral galaxy, much less massive, 150 billion solar masses, rich in star-forming regions. What makes Triangulum scientifically interesting is its complicated gravitational relationship with Andromeda. Some simulations suggest Triangulum may orbit Andromeda. It may be falling toward Andromeda. It may have passed through Andromeda in the past. It may join the Milky Way-Andromeda merger later. If true, this could mean the local group's future merger is not a duet, but a trio. The eventual galaxy formed from all three may resemble a giant elliptical with a swirling, chaotic halo and multiple merged black holes. Astronomers call this long-term structure the local group elliptical, or simply our future supergalaxy. The local group is not just a collection of luminous stars and gas. It is embedded in a far larger and heavier structure made of dark matter, a mysterious invisible substance that doesn't emit light but exerts gravity. Dark matter makes up about 85% of the local group's mass. It forms overlapping halos around Andromeda, the Milky Way, Triangulum, every dwarf galaxy, the entire local group itself. You can imagine dark matter as a giant, invisible spiderweb holding dozens of galaxies like dewdrops. The strands of this web guide their motions. Andromeda and the Milky Way are falling toward each other not just because of their own masses, but because they're sliding down the dark matter landscape, a gravitational valley carved out over billions of years. Without dark matter, the local group would not be gravitationally bound. Andromeda and the Milky Way would drift apart. The future merger would not occur. Dark matter is the quiet architect of our cosmic fate. While the local group is gravitationally bound, the universe as a whole is expanding. Over billions of years, distant galaxies accelerate away due to dark energy. This expansion has consequences. Galaxies outside the local group will eventually disappear beyond our cosmic horizon. The local group will become increasingly isolated. Gravitationally bound structures like the local group will merge internally. The future may look like this: local group, Milkdromeda, superlocal group, a single, massive elliptical galaxy containing the remnants of the Milky Way, Andromeda, Triangulum, dozens of dwarfs, trillions of stars, a vast dark matter halo. This merged structure will drift alone through an otherwise empty universe. In the extremely distant future, trillions of years ahead, the local group's supergalaxy may be the only visible structure left in the observable sky. Every other galaxy will be too far away to see. If intelligent life still exists at that time, their astronomers may conclude that the universe contains only one galaxy. They will have no observational evidence of cosmic expansion, no idea of the Big Bang, and no clue that the universe was once full of galaxies. We are lucky to live in an era when the cosmos is still visible. Let's summarize what makes Andromeda the local group's gravitational heavyweight. 1. Massive halo. Andromeda's dark matter halo is larger and heavier than the Milky Way's. 2. High satellite count it controls more dwarf galaxies. 3. Strong tidal influence. It shapes the orbits of nearby galaxies. 4. Future central position. After the merger, Andromeda's mass will help form the core of the new supergalaxy. 5. Cosmic cannibalism. Andromeda's history of absorbing dwarf galaxies has grown it into a dominant structure. If galaxies held elections, Andromeda would likely be voted most influential local group member. The local group contains many smaller galaxies that will eventually join the future Milkdromeda structure. Examples include the Large Magellanic Cloud, currently orbiting the Milky Way; Leo the Charners, a fast-moving dwarf; the Pegasus Dwarf; the Sagittarius Stream, already being digested by the Milky Way; Andromeda's many tiny satellites. Over billions of years, gravitational interactions will cause nearly every dwarf galaxy to fall inward. The local group is essentially a long-term gravitational vacuum cleaner. No small galaxy escapes forever. Beyond the local group lies the local sheet, then the local supercluster, and beyond that, an intricate cosmic web. But none of these structures are gravitationally bound. They will disperse as the universe expands. Only dense collections like the local group remain stable. This means that the Andromeda-Milky Way merger is just the first step of a larger evolutionary path. Galaxies merge. Groups merge. Cosmic isolation follows. In other words, the cosmos becomes emptier with time. Gravity wins locally, expansion wins globally. Andromeda's presence ensures that our section of the universe will eventually coalesce into a single massive galaxy. It is almost poetic, though we promised not to be too poetic. To tie this part together, Andromeda is the largest galaxy in the local group. Its gravity shapes the motion of dozens of neighbors. It has absorbed many galaxies already. It will merge with the Milky Way in about 4 to 5 billion years. The local group will eventually collapse into one enormous galaxy. The expanding universe will isolate this future galaxy from all others. Andromeda isn't just a nearby galaxy. It is the key to understanding the long-term fate of our cosmic neighborhood. In the last part, we will explore why Andromeda is scientifically important, what it teaches us about galaxy formation, and how studying it helps us understand the universe as a whole. We've talked about Andromeda's size, its structure, its stars, its dark matter halo, its satellites, its future collision with the Milky Way, and its role in the broader local group. But before we close this long exploration, it's worth asking a more philosophical and scientific question. Why does Andromeda matter? Why do astronomers spend so much time studying a galaxy 2.5 million light-years away? After all, space is full of galaxies. There are trillions of them. So, what makes this one so significant? The answer is surprisingly simple. Andromeda is special because it is close enough to study in high detail, large enough to be scientifically valuable, similar enough to the Milky Way to offer comparisons, and different enough to challenge our theories. This last part explores how Andromeda serves as a cosmic laboratory, and why its existence dramatically improves our understanding of galaxies, dark matter, cosmic evolution, star formation, and the long-term fate of the universe. In science, when we want to understand something complicated, we often compare it to something similar but not identical. This helps reveal which features are universal and which are unique. Andromeda plays the role of the Milky Way's control group. Both are large spiral galaxies. Both have supermassive black holes. Both have star-forming disks and bulges. Both have dark matter halos. Both have satellite galaxies, but they're also different in important ways. Andromeda is bigger. Andromeda has more mergers in its past. Andromeda's halo contains more metal-poor stars, suggesting earlier assembly. Andromeda's rotation and spiral structure differ from ours. By comparing the two, astronomers can isolate patterns in galaxy evolution. If two similar galaxies grew differently, why did they diverge? Answering that helps researchers understand what shapes spiral structures, why galaxies acquire certain halo properties, how frequently galaxies merge, how dark matter halos evolve, how star formation ramps up or shuts down. It is like having two ancient cities built in similar ways but with different histories. Studying both helps historians understand the general rules that shape civilizations. Modern astronomy has discovered an important truth. Large galaxies grow by eating smaller ones. This process, galactic cannibalism, leaves scars. Tidal streams, distorted stellar halos, compact leftover cores, chemical signatures of older populations. Andromeda displays these features more clearly than almost any other nearby galaxy. In fact, recent surveys like PANDAS, the Pan-Andromeda Archaeological Survey, found at least two major past mergers, dozens of stellar streams, a halo containing debris from many consumed dwarf galaxies, the remains of at least one galaxy nearly as large as a large Magellanic Cloud. Studying these tidal scars helps astronomers map out the sequence of Andromeda's past interactions. It's cosmic archaeology. Instead of digging up broken pottery, we're analyzing disrupted star clusters. These relics tell us when mergers happened, how violent they were, how much mass Andromeda gained, how galaxies change a shape after mergers. Because Andromeda is so close, we can detect details impossible to see in more distant galaxies. It's like having a giant museum exhibit next door. Andromeda contains regions of intense star formation. especially in its spiral arms and rings. Unlike the Milky Way, which hides much of its disk behind dust, Andromeda's structure is easier to observe across multiple wavelengths. Astronomers study star formation in Andromeda using ultraviolet imaging, young hot stars, infrared maps, warm dust clouds, radio telescopes, molecular gas needed for starbirth, H-alpha emission, active star-forming regions. These methods help answer questions like, why do some spiral arms form more stars than others? What triggers star formation bursts? How does star formation change after mergers? How long do giant molecular clouds survive before collapsing into stars? What regulates the star formation rate of a galaxy? Because Andromeda has experienced more recent mergers than the Milky Way. It shows different star-forming structures, including an enormous, nearly perfect star-forming ring created by a past collision. This ring has been studied extensively because it resembles a cosmic ripple frozen in time. Observing these natural experiments in Andromeda helps astronomers test theories of starbirth, cloud collapse, turbulence, and galaxy-wide feedback processes. At the center of most large galaxies lies a supermassive black hole. Andromeda's is about 100 million solar masses, roughly 25 times heavier than the Milky Way's central black hole, located inside a double nucleus structure. This peculiar structure contains two bright star clusters orbiting the central black hole at high speeds. The orbits create a lopsided appearance that puzzled astronomers for years. Why does Andromeda have a double nucleus? The leading theory is a past merger dumped a dense cluster of stars into the core, which became trapped in an elongated orbit around the black hole. This giant, unstable, eccentric disk allows astronomers to test how black holes influence surrounding stars, how mergers change galactic centers, how central star clusters form and evolve, how supermassive black holes grow over time. Andromeda gives us a rare view of a core that is more massive, more active in the past, more structurally complex than our own. It's a real-world example of what a galaxy looks like after absorbing another one. Dark matter remains one of the biggest mysteries in modern physics. We cannot see it directly, but we infer its existence because stars in galaxies move too fast to be held by visible matter alone. Galaxies orbit within larger gravitational halos. Gravitational lensing reveals missing mass. Cosmic structure formation simulations require it. Andromeda's proximity allows researchers to map its dark matter halo with unusually high resolution. We use stellar velocities, rotation curves, satellite galaxy orbits, gravitational lensing, the distribution of hot gas. These observations help evaluate competing dark matter theories. Cold dark matter, CDM, warm dark matter, WDM, self-interacting dark matter, SIDM, modified Newtonian dynamics, MON, a minority alternative. Because Andromeda is large, nearby, and well-measured, it provides an excellent case study for testing the shape and mass of dark matter halos. Its halo extends at least 1 million light-years, overlapping with the Milky Way's own halo. In fact, the two dark matter halos are already touching. In a sense, our galaxies are already colliding through their invisible components. Mapping these halos helps refine the amount of dark matter, its density profile, how it interacts with baryonic, normal matter, how mergers redistribute dark matter. Andromeda is a critical calibrator for cosmological simulations. Astronomers rarely get the chance to predict a major galactic event with high precision, But the Andromeda-Milky Way merger is one such case. This collision allows us to test long-term dynamical models. How will the stars rearrange? How long will the merger take? What will happen to the central black holes? Will star formation ignite or decline? What will the merged galaxy look like? Simulations suggest the first close pass will occur in upper 4 billion years. The galaxies will oscillate through each other. Tidal tails will stretch across hundreds of thousands of light years. After 16 billion years, the galaxies will merge into an elliptical shape. We will not be destroyed. Stars are too far apart for direct collisions. But our night sky will look spectacular. The Milky Way-Andromeda merger is one of the best modeled large-scale dynamical events in astronomy. Studying it helps refine N-body gravitational simulations, star distribution models, dark matter merger behavior, galaxy evolution theory. It is effectively a future laboratory experiment written into the sky. Andromeda helps answer major questions about the universe, including 1. How do galaxies grow over time? By mergers, gas inflow, star formation, tidal stripping. 2. How do disks survive despite constant disturbance? Andromeda reveals how resilient spirals can be. 3. What role do dark matter halos play? They shape the structure, rotation, and future of the galaxy. 4. How long can star formation last? Andromeda is transitioning from active star formation to a slower phase. 5. How do galaxies interact in groups? The local group, dominated by Andromeda and the Milky Way, is a perfect environment to model these interactions. 6. What will the universe look like in the far future? Isolated, filled with giant elliptical galaxies, the results of mergers like the Milky Way-Andromeda event. Andromeda has played a surprising role in shaping modern astronomy. In 964 CE, Persian astronomer al-Sufi described it as a little cloud. In 1923, Edwin Hubble proved it was a separate galaxy, not part of the Milky Way. This discovery exploded the size of the known universe. In the 20th and 21st centuries, space telescopes, Hubble, Spitzer, Galex, JWST, mapped Andromeda in unprecedented detail. Andromeda has been used to measure cosmic distances, refine the cosmic distance ladder, test stellar population models, study galactic halos, map intergalactic gas, calibrate galaxy formation simulations. It is arguably the most important galaxy in astronomy after our own. The big picture: why Andromeda matters. Summarizing the scientific value of studying Andromeda. It is the closest large galaxy, allowing detailed observation. It resembles the Milky Way, making comparisons meaningful. It challenges our models because it is not identical to our galaxy. It provides clues to galactic mergers, star formation, and dark matter. It shapes the local group's long-term evolution. It participates in a future cosmic event that astronomers can predict and model. It calibrates cosmology, helping refine our understanding of the universe. In short, Andromeda is a cosmic Rosetta Stone, a key to deciphering how galaxies form, evolve, and eventually fade into the distant future. Andromeda is not just a bright smudge in the night sky. It is a massive spiral galaxy, a holder of cosmic history, a future dance partner of the Milky Way, a laboratory for physics, a test case for cosmology, a messenger from the early universe, a blueprint for our galaxy's future. One of the most scientifically valuable objects we can observe. Our exploration of Andromeda, its structure, stars, dark matter, satellites, history, and future reveal something important about astronomy. To understand ourselves, we must look outward. Studying Andromeda gives us insight into our own galaxy, our cosmic neighborhood, and the universe we inhabit.